Imagine you're holding a stopwatch in one hand and a map of the Milky Way in the other. One of them feels honest. The other feels like a prank. Because a human lifetime is, what? 8 or 9 decades if you're lucky. But space is measured in light years, a unit that basically says, good luck. So here's the question we're really asking. How far could a human travel through space in one lifetime, if we play by the rules of physics? And those rules are strict. They don't care about courage, or budgets, or how inspiring the mission patch looks. At our current speeds, even the nearest star is not a trip. It's a family heirloom. You launch a ship today, and the arrival is someone else's problem, thousands of years later. But then, physics hands us a weird loophole. Not a cheat code, more like a trade offer. It goes like this. The faster you travel, the slower your time moves. Not in a poetic way. In a measurable GPS satellites need to correct for it way. And here's a twist you should keep in your pocket from the start. In principle, you can cross huge stretches of the universe in a single lifetime, as long as you accept that everyone you leave behind will age far more than you do. So the story splits into 2 routes. Route 1 is the slow way. You don't outrun time, you endure it. That's generation ships, hibernation, maybe sending machines instead of bodies. It's less epic hero, more very committed road trip with no return address. Route 2 is the fast way. Relativistic travel, time dilation, the strange math where a long distance shrinks for the traveler. It's the closest thing physics allows to time travel, except the direction is always forward, and the ticket is expensive. And expensive doesn't just mean money. It means energy. It means shielding, because at high speed even a speck of dust can hit like a bullet. It means radiation, heat, engineering headaches that don't care how optimistic we feel. So, by the end, we're going to answer 3 questions clearly. First, how far can we go with today's technology, honestly? Second, how far could we go if we could build near-light-speed ships, theoretically? And third, the quiet one. If you can travel that far but can't come back to your own time, what does one lifetime really mean? Hello and welcome to Sleepy Space Traveler. This channel was created as a quiet space for anyone who enjoys falling asleep to calm storytelling, peaceful narration, and soft explorations of science, the universe, and the mysteries around us. If this kind of content helps you relax, unwind, or fall asleep a little easier, I would really appreciate it if you could like this video and subscribe to the channel to help more people discover this space and help us continue creating these nightly journeys. Please let me know in the comments where you're watching from and what time it is for you right now. Thank you for being here. Alright, let's start where every space journey really begins. Not with rockets, with distance. We start with a reality check. Not to be mean, just to be honest. Because if we don't get the scale right at the beginning, everything else becomes space-flavored wishful thinking. We're going to answer one question first. What does far even mean in space? When you only have one lifetime. On Earth, far is a long drive, or a long flight. You can feel the distance in your bones. You can complain about it to strangers at the airport. Space doesn't give you that comfort. Space uses different units. Space makes distance feel less like geography and more like a dare. Let's start with the unit that shows up everywhere, the light year. A light year is not time. It's distance. It's how far light travels in 1 year. That's already weird because we use time to measure distance. But it's actually a pretty sensible choice. Light is the fastest thing we know how to use reliably. It's nature's speed limit for signals. So, if you're going to measure the universe, you measure it in how long light takes to cross it. Here's a way to picture it without a chalkboard. Imagine the fastest messenger you can hire is light itself. No traffic, no delays, no lunch breaks. If light takes 4 years to get somewhere, then anything that obeys physics will take 4 years or more. Usually more. Now, the nearest star system to the Sun is Proxima Centauri, a little over 4 light years away. That means even light needs over 4 years to make the trip. So, before we even talk about engines, that distance tells us something important. The nearest star isn't next door. It's more like next continent, except the ocean is empty and the boat can't stop. Now, let's talk speed. Humans love speed. We celebrate it. We name sports cars after it. We put it in movie titles. But space has a cruel sense of humor. It lets you go fast, and then it reminds you what fast actually means. Let's pin down a reference point. The speed of light is about 300,000 kilometers per second. That's roughly 186,000 miles per second. Light can circle Earth about 7.5 times in 1 second. That's not fast. Your brain is not built for this. So how fast do we go, really? A typical chemical rocket is great at escaping Earth, but it's not great at long-term cruising. Most of the magic happens at launch, when you burn fuel to get out of the gravity well. After that, you're mostly coasting, like throwing a baseball and hoping it keeps going forever. The fastest spacecraft humans have made so far have reached hundreds of thousands of miles per hour. That sounds huge. And it is, by Earth standards. But compared to light speed, it's tiny. It's like bragging you can sprint across your living room, when the real challenge is crossing the Pacific Ocean before dinner. This is where people get surprised. Even if you build a spacecraft that's the fastest thing we've ever launched, it still takes thousands of years to reach the nearest star. That's the basic dilemma. In one human lifetime, with today's tech, you don't reach the stars. You don't even get close. You get a respectable tour of our own solar system. And that's not nothing. Our solar system is enormous. The Sun, the planets, the moons, the asteroid belt, the Kuiper belt, this is a whole neighborhood. But it's still a neighborhood. If you want interstellar travel, you need one of 2 miracles. Miracle number 1, you go much, much faster. Miracle number 2, you stop caring about one lifetime and start caring about many lifetimes. We'll explore both. But first, we need to understand why going much faster is so hard. Because the obstacle isn't just engineering. The obstacle is physics plus energy, plus the fact that space is an unfriendly place to hit things at high speed. So let's talk about why rockets are limited. The main reason is brutally simple. Rockets carry their own fuel. That means every extra bit of speed costs more fuel. But adding more fuel increases your mass. And increasing mass means you need even more fuel to push it. And that means more mass. And now you're trapped in a loop. It's like trying to deliver a pizza, but every time you add more gas to your car gets heavier, so you need more gas, which makes it heavier, which makes you need more gas. At some point, you're basically driving a gas station. This isn't a joke. It's a real equation, and it's famous. It's called the rocket equation, and it's not your friend. The rocket equation says, if you want to go faster, you need exponentially more fuel, unless you can get a much higher exhaust velocity, meaning your engine throws propellant out the back incredibly fast. Chemical rockets throw exhaust out fast, but not fast enough for interstellar dreams. Ion engines can throw exhaust out much faster, which is great. But they produce tiny thrust. They're like a gentle electric fan pushing a cargo ship. If you run them for months or years, you can build up speed, but you're still nowhere near light speed. Solar sails are another clever idea. Instead of carrying fuel, you ride on sunlight. Light has momentum, and it can push a sail. It's real. It works. But sunlight gets weaker as you move away from the sun. And even near the sun, the push is gentle, like trying to cross a lake by blowing on a sheet of paper. Nuclear propulsion can help. Fission or fusion could give you more energy per kilogram than chemistry ever will. That's one of the big, maybe someday routes. But even then, getting to a significant fraction of light speed remains outrageously difficult. So, for part 1, here's the core concept we need locked in. Interstellar travel isn't mainly blocked by distance, it's blocked by speed. And speed is blocked by energy. Because kinetic energy grows fast, really fast. Energy scales with the square velocity in the everyday regime. Double your speed, you need 4 times the energy. Triple your speed, 9 times. And once you get close to light speed, relativity makes it even worse. The closer you get to light speed, the more energy you need for each extra bit of speed. The universe is basically saying, sure, you can try, but you'll pay per mile, and the price goes up the faster you go. A helpful analogy here is pushing a shopping cart. At first, it's easy. The cart starts rolling. Great. But imagine the cart gets more resistant the faster it goes. At 5 miles per hour, no big deal. At 20 miles per hour, it gets heavy. At 60, it feels like it weighs a ton. At 100, it might as well be welded to the floor. That's not exactly how relativity works mechanically, but it captures the vibe. Near light speed, nature makes acceleration painfully expensive. So, to answer the title question, how far could a human travel in one lifetime? We're forced into a fork in the road. Option A. You accept modest speeds, and you accept long travel times. That leads to generation ships, suspended animation, and sending descendants instead of yourself. Option B. You aim for relativistic speeds, where time behaves differently for the traveler. That's the route where one lifetime becomes a flexible idea. Not because you live longer, but because your clock and Earth's clock stop agreeing. Part 2 will be about that. But before we earn relativity, we need one more scale check, because it's the thing people underestimate most. The solar system is big, but it's tiny compared to the distance to even the nearest star. Here's a quick mental picture you can carry. Imagine the solar system is the size of a coin in your hand. Not Earth, not the Sun. The whole solar system out to the edge where the planets are. Now imagine the nearest star is several football fields away. That's the ratio we're dealing with. It's not that stars are far, it's that the space between star systems is mostly nothing, and it comes in industrial quantities. This is why our current space achievements, as impressive as they are, do not automatically scale to interstellar travel. We are great at climbing out of Earth's gravity well. We are getting better at navigating the solar system. But crossing the star-to-star gulf is a different sport entirely. So, if you're listening and thinking, okay, so the answer is basically not far, you're half right. With today's tech, one lifetime gets you deep into the solar system, maybe far beyond the outer planets if you're patient, but it does not get you to another star. Unless you change what one lifetime means. And that's the mystery we're about to open up. Because relativity does something strange and very real. It lets a traveler experience less time than the rest of the universe. The faster you go, the more dramatic it becomes. So the question isn't only, how far can a ship travel in 80 years? It's also, how far can you travel in 80 years of your own time, if time itself stretches? That's where the story gets properly wild, and still, somehow, remains physics. In Part 2, we'll build the key idea, time dilation, using examples that are real, measurable, and not just thought experiments. We'll talk about why GPS has to care about relativity. We'll talk about particles that live longer when they move fast. And then we'll use that same logic to sketch what a relativistic human road trip would actually look like. For now, keep one sentence in mind. Distance is the first barrier. Energy is the second barrier. Time is the third barrier, and time is the only one physics sometimes lets you negotiate. The next part is where the story stops being space is big and rockets are slow, and starts being, wait, time itself is negotiable? Not negotiable like a coupon. More like negotiable the way traffic laws are negotiable when you're in a helicopter. You're still obeying physics. You're just playing in a different regime. Here's the big idea we're building toward. If you travel fast enough, you don't experience time the same way as someone who stays home. Your clock runs slower compared to theirs. That's not a metaphor. That's a measurement. And it's the reason the phrase "in one lifetime" has two meanings in space travel. One lifetime for the people who stay on Earth. A different lifetime for the people on the ship. The weird part is that both are correct at the same time. Let's start with the most important thing to get straight. This is not about your feelings of time. It's not time flies when you're having fun. It's time on an actual clock. The kind of clock that does not care about your mood. Einstein's special relativity says, the speed of light is the same for all observers, no matter how they move. That single statement forces space and time to adjust so the universe stays consistent. And the adjustment is, moving clocks tick more slowly. If that sounds backwards, good. That means you are paying attention. Here's a simple analogy. Imagine the universe is a strict accountant. It has one rule. Everyone must agree on the speed of light. But different observers are moving relative to each other. They measure distances differently and times differently. So the universe does a kind of balancing act. If your motion makes a distance look shorter, then your time has to stretch so that light still covers that distance at the same speed. The books must balance. Now you might be thinking, fine, but is this real or just math? It's real. We don't have to trust Einstein because he had good hair or a good reputation. We trust him because we've tested these effects in multiple ways. One of the cleanest everyday examples is GPS. GPS satellites are moving fast relative to Earth, and they are also sitting higher in Earth's gravitational field. Both effects change how time passes for them compared to clocks on the ground. If engineers didn't correct for relativistic time differences, GPS would drift noticeably, by kilometers per day. Your phone would tell you you're in the middle of a lake while you're standing in a coffee shop holding a muffin. So, yes, relativity is real enough to keep you from getting lost. Another example comes from particle physics. High in Earth's atmosphere, cosmic rays smash into atoms and produce particles called muons. Muons have a very short lifetime when at rest. They should decay quickly and never reach the ground in large numbers. But they do reach the ground. Why? Because they're moving so fast that, from our point of view, their clocks run slow. They live longer in our frame. That's time dilation in action. So, the phenomenon is not a theory waiting for its big moment. It already has a job. Now, let's build the concept carefully, because we're going to use it later to calculate how far you can go. Time dilation depends on speed. The faster you move, the bigger the effect. At low everyday speeds, cars, planes, rockets going to the moon, it's tiny. But near the speed of light, it becomes dramatic. Here's the key intuition. As your ship approaches light speed, the outside universe seems to speed up compared to you. A way to hear that without panicking is this: your own time feels normal. Always. Your heartbeat feels normal. Your thoughts feel normal. Your coffee still gets cold at the same rate. But when you compare clocks with someone who stayed behind, you don't match. Their calendar races ahead. This is the famous twin paradox, though it's not really a paradox once you do the physics properly. Two twins start on Earth. One stays, one travels in a fast ship, turns around, and comes back. The traveling twin has aged less. People call it a paradox because they say, but motion is relative. From the ship, Earth was moving, so shouldn't Earth's clock run slow instead? That's where the turnaround matters. The traveling twin changes frames when accelerating and returning. The situation isn't symmetric. The twin who stays home remains in, approximately, one inertial frame the whole time. The traveler does not. If you want a simple life analogy, it's like two people comparing step counts. One person walks straight down one street. The other takes a route with a big detour and a U-turn. You can't treat those paths as identical just because both people moved relative to each other at some points. The geometry of space-time makes the straightest path maximize proper time. The stay-at-home twin follows the straighter path through space-time. The traveler takes a bent path. Less proper time passes for them. Now, for space travel, this has a startling implication. If you can build a ship that travels close to light speed, you can cross enormous distances while aging only decades. That sentence is both exciting and dangerous, so let's unpack it properly. Suppose you travel at 0.9 times the speed of light, 90% of light speed. What happens? From Earth's point of view, you move really fast, so you cover 0.9 light years per year. Great, but from your point of view, time is slowed relative to Earth. Earth clocks tick faster than yours. So while Earth might say the journey took, say, 10 years, you might experience much less. At 0.99 C, it becomes more extreme. At 0.999 C, it becomes absurd. This is how relativity makes one lifetime flexible. You can, in principle, travel to places that are thousands or millions of light years away and still experience only a few decades on board. But, and this is the part that keeps it from being a happy magic trick, Earth does not share your shortcut. In Earth's frame, the journey really does take thousands or millions of years. When you come back, if you can come back, Earth has moved on without you. That is the cost of the loophole. It's like taking a nap on an overnight bus, except you wake up and everyone else has lived through centuries. Now, we need one more concept before we start using this to estimate distances: acceleration. So far, we talked about traveling at a constant speed. But how do you get to that speed? In science fiction, ships jump to high velocity. In physics, you accelerate. And acceleration is where the story becomes more human, because there's a very practical comfort limit. G. G is Earth gravity. It's what you feel standing normally. If you built a ship that could accelerate at 1 g for long periods, the passengers would feel normal weight the whole time. You'd have artificial gravity without spinning the ship. Just point the engine in one direction and go. Here's why that matters. Constant acceleration changes everything about how far you can go in a given ship time. If you accelerate at 1 g for a while, then flip the ship and decelerate at 1 g, you can reach your destination quickly and arrive gently instead of blasting past it. This is the relativistic road trip plan. The dream itinerary looks like this. Accelerate at 1 g for half the trip. Flip around. Decelerate at 1 g for the second half. It's like driving to a destination. You press the gas at first, and then later you press the brake. Except here, the highway is empty space and the speeds get ambitious. Now comes the part where I'll keep the math light, because you're listening, not staring at equations, but you still deserve honesty. At 1 g, you reach very high speeds quickly. Not instantly, but quickly in human terms. In roughly a year of 1 g acceleration, you can get to a speed that is a significant fraction of light speed. And because relativity kicks in, the deeper you go into the trip, the more strange the clock comparison becomes. A helpful analogy. Imagine you're jogging on a moving walkway at an airport. At first, you're just jogging. Then the walkway starts speeding up. Then it speeds up more. Your jogging effort feels steady, but relative to the terminal, you're now moving ridiculously fast. If the walkway could speed up endlessly, you could cross the entire terminal in seconds without ever sprinting harder. In our universe, 1 g is your steady jog, and relativistic effects are the moving walkway under you. Except, unlike the airport, the moving walkway costs energy. A lot of energy. We'll talk about the energy bill later. For now, we just want to understand the time story. So let's state the key consequence in a clean, listenable form. If you travel near light speed, distant destinations become reachable in your lifetime because your time slows relative to the rest of the universe. But the universe does not slow down with you. It speeds up. That means the mission profile matters. If your goal is go far and never return, relativity is your friend. You can cross huge distances and still live out a human life on board. If your goal is go far and come back to the same civilization, relativity is your enemy. The faster you go, the more the homeworld races ahead. This is why relativistic travel is not just space travel. It's also a form of one-way time travel into the future. Not because you broke physics, but because you used it exactly as written. Now, in the next part, we'll turn this into numbers you can feel. We'll do a guided tour of what one lifetime can mean in ship time if you can maintain high acceleration and reach relativistic speeds. We'll look at specific destinations: the nearest star, the center of the Milky Way, Andromeda, and yes, the truly ridiculous one, the edge of the observable universe. We'll keep 2 clocks running the whole time: ship time, how long it feels for the traveler; Earth time, how long passes for everyone else. And we'll make the trade-off painfully clear. You can go very far, but you can't take your time with you. All right, let's cash in the weird promise we've been building toward. We've got 2 clocks on the table now. Your clock on the ship, and Earth's clock back home. They do not agree once you start moving fast. And that single fact changes what a lifetime can buy you. So instead of asking, how many light years can I travel in 80 years? We ask something more honest. How far can you go in 80 years of your own time, if you're willing to let the rest of the universe run ahead without you? Now we need a travel plan. Not a wish, a plan. The cleanest thought experiment is also the most comfortable for humans. Keep the ship accelerating at 1g, Earth gravity, so you feel normal weight inside. No spinning habitats, no floating toothbrushes. Just a steady push like you're standing on Earth. There's one catch, and it's a big one. You can't accelerate forever in the same direction unless you want to zoom past your destination and keep going into the cosmic parking lot. So the standard nice plan looks like this. You accelerate for the first half of the trip, then you flip the ship around, then you decelerate for the second half. It's the same logic as driving to a town on a highway. You don't keep pressing the gas until you reach the town and then magically stop. You speed up, then later you brake. If you do this at 1 hour, something almost unfair happens. In your own time, you reach relativistic speeds quickly. Not instantly, but quickly enough to matter. Within about a year of constant 1g acceleration, you're already moving so fast that time dilation is not a tiny correction anymore. It starts changing the whole accounting of distance and time. Here's the best way to hold this in your head. The faster you go, the more the outside universe seems to fast forward compared to you. Your body stays normal. Your heartbeat stays normal. Your meals take the same amount of time to eat. Your sleep still takes 8 hours. But when you look back at Earth's calendar, if you could, Earth is burning through time faster than you are. Now, we'll do this with concrete destinations, because that's where the intuition locks in. First stop, the nearest star. Proxima Centauri is a little over 4 light years away. If you were traveling at a constant speed, this would be straightforward. At half the speed of light, it takes a bit over 8 years by Earth clocks. At 90% of light speed, it takes a bit under 5 years. But with the 1g accelerate then brake plan, you don't spend the whole trip at one speed. You start slow, then go faster and faster, then slow down again. That makes the math more complex, but the conclusion is simple. For nearby stars, relativity helps a little, but not dramatically. The trip is still measured in years for you, and also years for Earth. So, for the nearest star, you don't get the full relativity miracle. You get a modest discount. And that's fine. A few years to another star is still incredible. But the real magic shows up as the destinations get bigger. Because once distances become thousands of light years, you start spending much of the trip near light speed. That's when the time gap between ship and Earth gets enormous. So let's aim bigger. Now think about crossing the Milky Way. The center of our galaxy is roughly 26,000 to 28,000 light-years away, depending on which numbers you use. That is so far that if you traveled with today's best spacecraft speeds, the trip would take longer than recorded human history by a factor that's honestly rude. But at relativistic speeds, with steady acceleration and deceleration, the story changes in a way that feels like science fiction but is pure relativity. From Earth's point of view, you cannot beat the basic fact that the galaxy is tens of thousands of light-years across. No matter what you do, Earth sees the trip taking tens of thousands of years. Even if you go very close to light speed, Earth time is still basically distance divided by nearly c. So, if you leave Earth and head to the galactic center and later come back, Earth will have aged by something like 50,000 years for a round trip. Civilization will not be waiting with balloons. You will be archaeology. But, from your point of view, time dilation changes your experience dramatically. If you can sustain 1g acceleration for a long period, you can make that one-way journey in something like a few decades of ship time. Not thousands of years. Decades. This is the first big aha moment. The galaxy can be crossed within a human lifetime, your lifetime, if you accept that you will be stepping into the far future of Earth. A useful analogy is taking a train that goes so fast that everyone outside ages while you barely do. You step on the train in your 20s, and when you step off, you're in your 40s. But outside the train, entire dynasties have come and gone. Relativity gives you a way to trade everyone else's time for your distance. Now, let's push even further, because the next step is where the word lifetime starts to feel like a joke the universe is telling with a straight face. Next stop, another galaxy. Andromeda is about 2.5 million light-years away. It is our nearest large neighboring galaxy, and it's coming toward us slowly because gravity is doing its thing on cosmic scales. If you travel to Andromeda at any speed less than light, Earth sees the trip taking millions of years. That's unavoidable. But on the ship, if you can get close enough to light speed, time dilation can reduce your experienced travel time to something like a few decades. Still a long trip for you, but not longer than a human life. So you could leave Earth at 25 years old, travel to Andromeda, and arrive still alive, still you, still within one lifespan, while Earth, meanwhile, has run forward by millions of years. In Earth's frame, it's as if you vanished into the future. In your frame, it's a very long commute with a very strange view. This is where people often ask, how can that possibly be consistent? Doesn't that mean you traveled faster than light? No, you never outrun light locally. In your own local neighborhood, light still wins every race. The trick is that time is not the same for you and for Earth. The distance is measured in Earth's frame as 2.5 million light-years. But in your frame, because of relativistic effects, the distance you need to cross is effectively shorter. Not because space physically compresses like a spring, but because space-time geometry makes different observers slice up space and time differently. A life analogy helps here. Imagine two people watching the same parade from different places. One watches from the sidewalk, the other watches from a drone moving quickly along the road. The sidewalk observer measures the parade as 10 blocks long. The drone observer measures it differently because they're moving with the flow, and their perspective compresses the road. It's not a perfect analogy, but it captures the basic idea. Distance depends on the frame you're using. In relativity, that effect is called length contraction, and it works hand in hand with time dilation. Together, they allow a traveler to experience far less time for the same journey that takes vast time in the Earth frame. Now, if you've been quietly thinking, okay, so in principle I could go anywhere, you're close to the deepest twist in this whole story. Because if you can push close enough to light speed, the reachable universe in a lifetime becomes enormous. So let's say the quiet part out loud. In principle, you could travel to places billions of light years away and still experience only decades on board, if you can sustain the acceleration and survive the environment. You could even aim for distances comparable to the observable universe. But there's a subtle catch. The observable universe is not just a static sphere of stuff sitting there. The universe is expanding. Some regions are moving away from us so fast, due to the expansion of space, that even light emitted today will never reach us. That means there are limits not just from your engine, but from cosmology itself. So the real version of how far can you go has two answers. How far can you go according to your ship clock using relativity? Potentially very far. How far can you go and still ever communicate with home or return to anything recognizable? Much less far. Because the moment you lean on strong time dilation, you're basically choosing to leave your home era behind. This is where the two-clock view becomes emotionally important. Not emotional in a sentimental way, more like the cold clarity of what the physics implies. In ship time, you can reach the galactic center in a few decades. In Earth time, you arrive tens of thousands of years later. In ship time, you can reach Andromeda in a few decades. In Earth time, you arrive millions of years later. The universe will still exist. But home will not. A nice way to summarize this without drama is, relativity lets you buy distance using everyone else's time. Now, there's another question listeners always have at this point. If it's just time dilation, why don't we notice it in everyday life? We do. It's just tiny. At car speeds, time dilation is ridiculously small. Your clock and your friend's clock stay basically locked together. The effect is real, but it's buried under the noise of ordinary life. You need either extreme speed or extreme precision to see it. GPS has extreme precision. Particle physics has extreme speed. Your commute has neither. So, the relativity road trip isn't fantasy because relativity is untested. It's fantasy because we can't build the ship. And now we've reached the exact moment where the story naturally pivots from what the universe allows to what we can actually do. Because so far, we've been living in the clean world of thought experiments. Perfect engines, endless fuel, no radiation disasters, no collisions, no maintenance failures, no cooling problems, no human psychology. And a ship that politely accelerates at 1G for years like it's no big deal. Real space travel is not that polite. The next piece of the story is the bill, the energy bill, the engineering bill. The dust grain at 0.9 C is not a dust grain anymore bill, and that's where the dream gets tested. So the next step is to ask a brutally practical question. What kind of engine could possibly do this? How much energy would it take? And what does space do to you when you plow through it at a speed where even sparse gas becomes a radiation hazard? That's where the romance of the galaxy road trip meets the physics of everything becomes a bullet. And that's where we go next. Okay. Now we pay the bill. Up to this point, we've been living in the clean, polite universe of thought experiments. A ship that accelerates at Earth gravity for years. A crew that stays comfortable. A destination that sits still and waits. And an engine that somehow keeps pushing like it has an endless supply of motivation and fuel. Real space travel is where physics stops being inspirational and starts being an accountant. Because getting to near light speed isn't just hard. It's hard in multiple different currencies at once: energy, mass, heat, shielding, and survival. Let's start with the most brutal truth in the whole topic. Going fast is not the main problem. Stopping is. If you want to travel to another star and arrive in one piece, you don't just need enough energy to speed up. You need enough energy to slow down again. Unless you're okay with your mission ending as a very fast flyby and a very short data set. This doubles the challenge right away. It's like planning a road trip where you can accelerate using fuel, but you also have to pay fuel to brake. Most cars brake for free by dumping energy as heat into the air. Space does not give you free braking unless you have something to push against. So you need a propulsion system that can do both. Accelerate and decelerate for years. Now let's talk about rockets again, but in the simplest possible terms. A rocket works by throwing mass out the back. You gain momentum forward. That's it. That's the whole trick. The problem is that if you want to throw mass out the back fast enough to reach relativistic speeds, you need an engine with insanely high exhaust velocity. Chemical rockets are nowhere close. They're excellent for launching off planets. They are not interstellar engines. Ion engines throw propellant out much faster, which is good, but their thrust is tiny. They're like a slow, steady push. Great for gradual deep space missions. Not great for, let's get to 0.5 C before lunch. So you look for engines with far more energy per kilogram of fuel. And the menu becomes something like this: nuclear fission, nuclear fusion, antimatter, and then a few exotic ideas that mostly exist as math and hope. Fission is what we use in nuclear power plants. It releases a lot more energy than chemical reactions. Fusion is what powers the sun. It releases even more energy per kilogram in principle, and it produces less long-lived radioactive waste. Antimatter is the ultimate. When matter meets antimatter, almost all the mass turns into energy. Here's a simple analogy for the energy ladder. Chemical fuel is like burning wood. Fission is like splitting a bank vault full of energy. Fusion is like tapping a star in a bottle. Antimatter is like converting the bank vault itself into pure electricity. Now, here's the catch. Even star in a bottle is not automatically enough if you want near light speed with a large ship. Because the closer you get to light speed, the more energy each extra bit of speed costs. The universe adds a premium fee near the limit, and even before we reach that extreme, the numbers are already staggering. A helpful way to feel it is this. Kinetic energy at high speed is not like paying for gas. It's like paying for gas where the price quadruples every time you double your speed. Then it gets worse near light speed. It's a brutally non-linear climb. So if someone says, "Why don't we just build a bigger rocket?" the honest answer is because bigger isn't enough. You need different. Now, let's walk through the most discussed realistic-ish propulsion ideas and what each one buys you. Fusion rockets are the classic dream for interstellar travel. The idea is to carry fusion fuel, often isotopes like deuterium and helium-3 or other combinations, and use fusion reactions to produce high-energy exhaust. If you can do that efficiently, you can get much higher exhaust velocity than chemistry and potentially reach meaningful fractions of light speed. But fusion is hard in the most annoying way. It's not that fusion doesn't work. It works great in the sun. It works in hydrogen bombs. The challenge is controlled, sustained fusion in a compact system that can run reliably for years, while also being lightweight enough to be a spacecraft. Fusion on Earth is already a hero project. Fusion in a spaceship is that plus vibrations, radiation, limited mass, limited repair options, and no ability to pull over when something overheats. If fusion works, you might reach speeds like a few % of light speed, maybe more for lightweight probes. That's enough to reach nearby stars in decades to centuries by Earth time. Still not one lifetime unless you stretch the definition using generation ships or hibernation. But it moves the needle from thousands of years to maybe a human plan. Then there are laser-driven light sails, which are a clever cheat. Instead of carrying fuel, you let something else provide the energy. You build an ultra-thin reflective sail and blast it with a powerful laser from the solar system. The sail gets pushed by photons. No onboard propellant. The ship can be tiny. Very tiny. More like a chip with a sail than a crewed vehicle. This is promising for small probes because it sidesteps the rocket equation in a big way. The downside is also obvious. It's hard to accelerate something heavy, like a crewed ship, using light pressure unless you have truly insane laser power and a sail the size of a small country. And even if you can accelerate, you still have the stopping problem. A laser can push you outward from home. It's not easy to use it to brake at the destination. You need another laser array out there, or some kind of clever deceleration method, like using the destination star's light or magnetic fields. That's possible in theory, but it's not a simple arrive and park. So, light sails are a strong candidate for unmanned interstellar probes. For humans, they are more like a hint than a plan. Then we have antimatter, the if we could do it, it would be amazing option. Antimatter has incredible energy density. A small amount contains the energy equivalent of a lot of conventional fuel. The problem is that antimatter is not something you mine. You have to make it. Making it takes energy, and current methods are extremely inefficient. Also, antimatter wants to annihilate with normal matter on contact, which is inconvenient. When your ship is made of normal matter, and your crew is also normal matter. So, antimatter gives you huge theoretical capability with huge practical obstacles: production, storage, safety, and the difficulty of turning that energy into directed thrust efficiently. It's like having the world's best gasoline, except it costs a fortune to produce, evaporates if you blink wrong, and might delete your vehicle from existence if your tank develops a leak. Now we shift from engines to another kind of problem. Even if you have the engine, space is not empty. We say space is empty because compared to Earth's atmosphere, it is. But if you're moving at a significant fraction of light speed, almost nothing stops being almost. Here's the key idea. At high speed, tiny things hit like big things. A grain of dust at highway speed is a mild nuisance. A grain of dust at orbital speed can be a problem. A grain of dust at 1/10 of light speed is a grenade. At half-light speed, it's closer to a nightmare. And it's not just dust. Even individual atoms of hydrogen, spread thinly through interstellar space, become dangerous because of the relative energy when you plow into them at near-light speed. A good analogy is rain on a car windshield. If you're walking, rain is just rain. If you're biking fast, rain stings. If you're driving on the highway, rain becomes a constant battering. Now imagine you're driving so fast that each raindrop hits like a paintball. That's what the interstellar medium becomes. Not because space got thicker, but because you're moving through it at ridiculous speed. This creates two huge issues for relativistic travel. First, shielding. You need a front of the ship that can absorb impacts and radiation, but shielding adds mass. More mass means more energy. More energy means bigger engines. Bigger engines mean more mass. You can see how the loop tries to eat you alive. Second, radiation. At high speed, particles you run into can create showers of secondary particles. And there's also a background you can't avoid. The cosmic microwave background, the faint glow left over from the early universe. In our everyday frame, it's harmless microwave radiation. If you travel fast enough, that radiation gets blue-shifted, pushed to higher and higher energies in your forward direction. So, the universe starts throwing a wind of high-energy radiation at the nose of your ship simply because you're moving fast through the cosmic background. If that sounds unfair, yes. Physics is not a customer service business. And then there's heat. Every inefficiency becomes heat. Every interaction with incoming particles becomes heat. Every bit of shielding that absorbs energy has to dump that energy somewhere. In space, your main way to dump heat is radiation, glowing it away. That takes large radiators. Large radiators add mass and surface area and vulnerability. Again, the loop. So, even before you get to, could we build the engine, you run into, could we keep the ship from turning into a high-speed microwave oven full of humans? Now, let's add one more complication. Humans. Humans need life support, redundancy, spare parts, medical care, food systems, psychological stability, and a reason not to start a very heated argument about music playlists in year 12 of the voyage. A crewed ship is not a probe with a camera. It's a small traveling ecosystem. This matters because a lot of the engine ideas that look plausible for probes do not scale nicely to human missions. You can blast a gram-scale sail to a fraction of light speed. You cannot casually blast a 1,000,000-ton habitat without rewriting our relationship with energy. So, if we're staying honest, we need to separate two kinds of one-lifetime missions. One lifetime for a tiny robotic probe. One lifetime for a crewed ship with humans on board. The first might be plausible sooner. The second is far more demanding. This is why many serious discussions of how far could humans travel start sounding like this. Within one lifetime, humans can go far within the solar system with plausible technology. To go to other stars, we may need new propulsion and new strategies for humans. To go relativistically, we may need a civilization-level energy budget and engineering capabilities beyond what we currently have. Now, that sounds like a downer. It's not meant to be. It's actually the point where the story gets interesting again, because it forces us to broaden what human travel can mean. If a single human body is hard to move to the stars, maybe we change the mission architecture. Maybe we slow down and accept centuries. Maybe we send many generations. Maybe we hibernate. Maybe we send embryos and automation. Maybe we send AI. Or maybe we accept the relativistic route as a one-way expedition into the far future, where the goal isn't return home, but reach a place and start something new. Each of those options has a very different relationship with the phrase "in one lifetime." And that's the natural next step. Because the story isn't only about physics limits, it's about how you design a mission around those limits. So the next question is not, how fast can we go? But if we can't get a crewed ship near light speed anytime soon, what's the most realistic way for humans, or human civilization, to reach another star? That takes us into slower travel, generation ships, hibernation, and the uncomfortable but practical possibility that the first interstellar travelers might not be biological at all. And that's where we go next. Once you've stared at the energy bill and the shielding bill and the dust grain becomes a bullet bill, the conversation naturally changes. Not because we're giving up, but because we're being honest about what kind of problem this is. Relativistic travel with living humans is not just a hard engineering project. It's a civilization scale project. It asks for absurd energy, absurd reliability, and absurd protection against an environment that becomes hostile simply because you're moving fast. So, if you want humans reaching other stars on a timescale that feels remotely realistic, you start considering slower strategies. Strategies that don't require bending physics to the breaking point. This is the part of the story where the ship stops being a rocket with seats and becomes a moving world. The first big idea is the generation ship. A generation ship is exactly what it sounds like. A ship that takes so long to reach its destination that the people who launch it won't be the people who arrive. The ship is not a vehicle you ride. It's a habitat you live in. A tiny artificial planet with a course. If that sounds extreme, it is. But it's also, in some ways, the most straightforward option. It doesn't require near-light-speed travel. It doesn't require time dilation tricks. It requires endurance. Here's an analogy that fits the listening vibe. Imagine you're sending a ship across an ocean that takes 400 years to cross. Nobody alive has ever done it. Nobody alive will see it finish. So you don't send passengers. You send a colony, and you make sure the ship can farm, repair itself, recycle everything, educate children, and keep people sane for centuries. That's a generation ship. The physics side of generation ships is almost boring compared to the psychology and biology side. The ship could travel at 1% of light speed, still unimaginably fast by our standards, and reach the nearest stars in a few hundred years. That's slow for space, but it's fast enough to be a human project if your civilization can think in centuries. The problem is that a generation ship is a social experiment on the hardest possible difficulty setting. You need a population large enough to remain healthy and stable over many generations. Too small, and you run into genetic bottlenecks, social fragility, and the one bad decade ruins everything problem. Too large, and the ship becomes enormous, and then every engineering challenge multiplies, and then you hit the human questions that don't appear in rocket equations. Who gets to be born on the ship? What laws do they live under? Do they have the right to turn around? Do they have the right to stop the mission? Because from their perspective, the ship is not a mission, it's home. That's not just a moral issue, it's a practical one. If you build a generation ship, you need the culture on board to sustain itself for centuries. That means education systems, governance, conflict resolution, meaning-making. People need a reason to keep the project alive. You can't power a generation ship on fuel alone. You power it on continuity. Now, if that sounds like a lot to ask of humans, which, yes, it leads to the next strategy. Reduce the number of awake humans. This is where ideas like suspended animation or hibernation enter. We don't currently know how to put a healthy adult human into deep, safe hibernation for decades, and then wake them up like nothing happened. But nature does give us hints. Some animals slow their metabolism dramatically. Medical science already uses targeted temperature management in certain contexts, cooling the body to reduce damage after trauma. Researchers also explore torpor-like states for long-duration missions, because if you can keep a crew in low metabolic mode, you reduce food, water, oxygen, and psychological strain. For a listening analogy, think of it like putting your laptop into sleep mode rather than leaving it running at full power for months. Same machine, far less resource use. But humans are not laptops, and biology is not polite. Long-term sleep brings risks: muscle loss, bone density loss, immune system changes, blood clots, brain effects, and the huge question of how to keep someone healthy when their body isn't doing normal maintenance. So, hibernation is a maybe. It's not a current plan, but it's the kind of maybe that could transform interstellar travel, because it changes the problem from multi-century society in a box to long cruise with periodic maintenance. If you could do that safely, suddenly a ship traveling slowly could still deliver living humans to another star within the traveler's felt experience. They would spend most of the trip asleep. Their lifetime clock would be mostly paused. But even if hibernation becomes possible, you still have the mechanical reliability problem. You still need a ship that can stay functional for decades or centuries. You need self-repair, redundancy, and the ability to handle unexpected failures without Earth-based help. This is where the conversation gets even more pragmatic and a bit less biological. Maybe the first interstellar travelers won't be humans at all. Not because humans are bad, because humans are fragile. A robotic probe doesn't need air, water, food, or a functioning mental health support system. It doesn't care if the trip takes 200 years. It doesn't get bored. It doesn't develop osteoporosis. It doesn't need to be shielded to the same standard as living tissue. It can tolerate radiation that would be lethal to us. This is why a lot of serious interstellar proposals start with probes. But then you run into the identity question. If the probe carries human minds, does that count as humans traveling? This sounds like philosophy until you remember how much of you is information. Your memories, your personality, your skills, your preferences, the pattern. If you could preserve that pattern and run it on a different substrate, is it still you? We don't have that technology. We don't know if it will ever be possible. But it's a natural place the discussion goes because physics and engineering keep pushing us there. A middle ground version is simpler and more plausible. Send AI or automated systems to build infrastructure first. Imagine sending autonomous machines to another star system with one task: build. Build solar collectors, build habitats, build factories, build fuel depots, prepare a destination. Then, later, maybe much later, send humans, or send embryos, or send something like a starter kit for biology. This kind of plan is sometimes called seed ships, and it sidesteps one of the biggest immediate barriers: keeping living humans alive for the whole journey. It's like sending a construction crew ahead of time so that when the family arrives, the house already exists. Now, there's one more twist that people don't always expect. Even if you travel slowly, you still have a time problem. Just a different time problem. Slow interstellar missions require civilization-level patience. They also require political stability. A project that takes 300 years must survive changing governments, economic crises, cultural shifts, wars, and the simple reality that future generations may not care about the dream you started with. So, even slow and steady isn't automatically easier. It's easier in physics, harder in sociology. And that brings us back to the original question in a sharper form. How far could humans travel in one lifetime? Isn't only about distance and speed. It's also about what you mean by humans and what you mean by lifetime. If you mean a single biological person, awake the whole time, staying in sync with Earth time, the answer is far inside the solar system, and not to other stars with today's tech. If you mean a single biological person, using relativity to stretch their reach by time dilation, the answer becomes, in principle, extremely far, but at the cost of returning to a future where everything is different. If you mean human civilization, our culture, our genes, our descendants, then the reachable distance grows enormously, because now you can use generation ships, slow cruises, and timescales longer than one person. And if you mean human intelligence and identity preserved as information, then the lifetime question becomes something else entirely. All of these are different answers to the same question, and each one is legitimate depending on what you care about. This is the point where the story naturally tightens toward a conclusion. We've mapped the options. We've seen the costs. The last step is to put the whole thing in perspective, the traveler's paradox. Because the strangest result of all isn't that space is large or rockets are weak. It's that physics gives you a kind of bargain. You can go far, or you can stay connected to your time. But you don't get both. And the moment you accept that, one lifetime stops being a fixed ruler and becomes a choice about which clock you want to live by. That's where we're headed next. Yes, this is the final section. It's the ending that ties the whole story together and gives you a clean, memorable answer to the question. You can think of it as the moment we stop shopping for engines and start asking what the journey actually means. There's a strange moment in this topic where the math gets so powerful that it feels like it should solve everything. Time dilation is real. It's tested. It's built into technology we use every day, and in theory, it lets you cross distances that would normally take thousands or millions of years, while you experience only decades. So you'd think the conclusion would be, great, we can go anywhere. But the universe is not that generous. It always charges a price. And the price here isn't only energy. It's not only shielding. It's not only engineering. The price is time itself. Because there are two different meanings of in one lifetime, and they lead to two different kinds of travel. If you mean one lifetime on Earth's calendar, then the answer is blunt. With any technology we can realistically imagine in the near future, you stay inside the solar system. You can go far by human standards, outer planets, moons, deep space, but the stars remain out of reach within 80 or 90 Earth years. If you mean one lifetime by the traveler's clock, then the answer changes dramatically. In principle, you can reach other star systems, cross the galaxy, even reach other galaxies, without dying of old age. As long as you can get close to light speed and survive the trip. And that's where the traveler's paradox appears. The paradox is not a contradiction in physics. It's a contradiction in human expectations. We expect travel to be about distance, but at relativistic speeds, travel is also about which era you're choosing to live in. A fast journey is not just a journey through space. It's a one-way jump into the future of everyone you left behind. If you leave Earth and do a high-speed, long-distance trip, you don't return later. You return to a different civilization, a different world, possibly a different species, if enough time passes. This is why the most honest version of the question is not, how far can you go? But, how far can you go and still remain part of the same story? And the answer is, not very far, once you demand that you come back to your own time. Relativity is a bridge and a wall at the same time. It lets you cross space, but it separates timelines. That's the deep shape of the problem. Now, there's a second conclusion hiding underneath that one, and it's just as important. People often talk about the limits of a human lifetime, as if a lifetime is a fixed container. But in space, the container isn't fixed. The definition shifts depending on your speed, your mission design, and your relationship to home. If you travel slowly, one lifetime belongs to Earth. If you travel fast, one lifetime belongs to the ship. And if you travel with generation ships, one lifetime stops being the unit. The unit becomes a lineage. So the final answer depends on which version you want. If you want the cleanest, simplest summary, one you could say out loud in a single breath. It's this. In one lifetime, a human can explore the solar system with plausible technology. In one lifetime of ship time, a human could reach vastly farther, possibly across the galaxy, if we could build near-light-speed travel. But the faster you go, the more you leave your home era behind, and the less returning means what it used to mean. That's not a depressing conclusion. It's a clarifying one. It tells you what the universe allows and what the universe doesn't. The universe does not say, no, you can't go. The universe says, you can go, but you will pay. And that payment comes in forms we're not used to paying. Not just fuel, but time. Not just engineering, but separation from your own history. One last perspective helps keep this from feeling like a wall. We already travel through space on cosmic scales without noticing. Earth is moving around the Sun at about 30 kilometers per second. The Sun is orbiting the Milky Way. The whole galaxy moves through the local universe. In the broadest sense, every human life already includes an enormous journey through space. We're just doing it on a ship called Earth, with a very stable life support system and a convenient atmosphere. Interstellar travel would simply be taking responsibility for the steering. And whether we ever do it with living humans, or with robots, or with future descendants, or with some form of preserved intelligence, the deeper point remains the same. Space is not unreachable because it's too far. It's unreachable because doing it within a single human life requires either extreme speed or extreme patience. And both demand a level of technology and coordination we haven't reached yet. But this is the part where history gives us a quiet nudge. Humanity has never been good at staying in one place when there's a horizon. We crossed oceans with ships that had terrible survival rates. We learned to fly. We went to the moon with computers weaker than a modern phone. We keep building ladders toward things that used to be myths. So the final note of this story isn't "we can't." It's "we can't yet." And maybe that's the best ending a scientific story can give you. Not a promise. Not a fantasy. A map. A map of what's physically possible, what's currently impractical, and what the universe will charge you if you insist on going anyway.